Okay, so we're going to follow up with set theory. So let's fix some terminology. And core concepts. So we're going to talk about set theory and the axioms of probability. They're very closely connected. And extremely important to be 100% well-versed in this terminology and these concepts to be able to really understand the key ideas in probability. Okay, first we've already defined, and we will define formally here the sample space. Sample space, the collection of all possible outcomes. So outcomes, you can think of them as like the atomic events in a probability experiment. We write this set as omega. So what do I mean by the atomic events? When we're rolling two dice, the number on die one and the number on die two, the pair, that pair is an outcome. That's as granular as we can get on that experiment, on that roll of the dice. The count, the number, the sum of the two is not an atomic outcome. So if we add them up and they add up to 6, there are multiple different outcomes that can give us that sum, right? 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. There are 5 different possible outcomes that can describe that event. And that's the term. The next term is the term event, which we've already seen before. Event is a subset of the sample space. So this is a set of possible outcomes, subset of possible outcomes. So it consists of outcomes, and if the outcome, let me define outcome, okay. So an outcome is an element of the sample space. So we would write this as omega, little omega is an element of omega. So all of the 36 different pairings of two dice, each one of those is an element of the set, and each one of those is an outcome. An event is a subset of omega, and if the outcome omega is in the event, let me do this. We'll write this as E for event is a subset of omega, saying that E is everything inside of E is also inside of omega. If the outcome omega is in E, then E occurs. What do I mean by that? In this case here, this is an event, but we're going to roll the dice, and we're only going to see at most one of those possible outcomes. It's not possible for every one of them or even two of them to occur. We're going to see exactly one outcome of the black die and the white die. So when we do that, let's say we roll a 1, black is 1, white is 2, a 1, 2. That element, right, which is right here, is in the set E. It's in the event. And so we can say the event occurred, which means we can say that the black die was an ace. If the outcome is, let's say, a 3, 2, so the black was 3 and the white was 2, that is not in E, and so we say that E did not occur. So that's the terminology. So if the outcome omega is not in E, then E does not occur. Okay, so that's the terminology. Now, let's translate all of this into set theoretic language. Okay. So here's what we're going to do is we're going to have all different types of language. We're going to have event language, which is what we talk about in probability. It's the way that we can intuitively communicate about this stuff. We can have set language. Put this on two different lines. So event language, set language, and this is going to be a table for us. There's going to be set notation. There's going to be the definition. And we can visualize it with a Venn diagram. So it's going to be a very important and useful table for us. Okay. So let's start. Sample space. In event language, it's the sample space, the set of all possible outcomes. In set language, it's just a universal set. So it's everything. So it's the set of it's everything we can possibly talk about. It's the universe of discourse. In set notation, we can write it, we generally in probability write it as omega. You might also see it written as capital S. Definition, it's really just a collection of distinct objects. Objects or elements. And the way we write this as a Venn diagram is I'm going to represent as a rectangle. And it's a rectangle. I'm going to use this rectangle throughout this. So we're going to be seeing a lot of rectangles. And let me copy a bunch of these down just to get ready. All right, that should be good for now. So first, this rectangle, and what is the set? It's everything in the set. So it's the entire set. Everything. So everything, that's the sample space. All right, now an event, in event language, is a subset. It's just a subset of omega. We're gonna write these using capital letters, usually at the beginning of the alphabet. Okay. So these are capital letters, A, B, etc. And to denote that it's a subset of omega, it's A is a subset of omega. So that's what it is. It's just by definition is we can draw, let's say, some area inside of omega, call it A. And the event is the stuff that's inside of that A. Okay. Now we're going to talk about a couple of special types of events. There's the impossible event, also known as the null event. Null, N-U-L-L. as a set, this is just called the empty set. We denote it as a circle with a line through it to indicate there's nothing in it. By definition, this is the set with no elements. So it has nothing in it. So the picture is just nothing. It is still a set, even though there's nothing in it. Okay. So it can also be written as just two curly braces. So we usually, if we want to write a set explicitly as the elements it contains, we use the curly brackets and we write the elements inside. Here we have the curly brackets and there's nothing inside because there's no elements in the set. The event that A does not occur in set language is called A complement. So think of it as it's the complementary set to A. We write it as A with a superscript C. And as the definition is, what is the complementary set to A? Well, it's the set of all elements in omega such that the elements are not in A. So take this example up above. We have A here. This is A. What's A complement? Well, I need a thin pencil here. A complement is everything in omega that's not an A. So it's everything else. That's A complement. Okay. So A occurs if something in A happens. A does not occur if something in A complement happens. Okay. Mutually exclusive. So A and B are mutually exclusive. A and B are mutually exclusive in set theoretic language is to say that A and B are disjoint. By definition, this means that their intersection is empty. We have to define what intersection means in a second. But what this is saying is that there's no overlap. So we have A, we have B. I'll keep this as a circle, although they don't have to be circle. This is just a visual diagram, of course. I have A and I have B. And there's no overlap between them. There's no element in A that's also in B. There's no element in B that's also in A. So A and B, at least one of A and B occur. This is called A union B, written as A U B. Little u is like a union. It's called a union sign. What is this as a set? This is the set of X, set of elements, such that either X is in A, either X is in B, or possibly both. Okay, so if I have A and B here, let me I'm gonna use that for next. So again, if this is A and B, then what is their union? The union is all of the stuff that's in at least one of A and B, including the overlap, so it could be in both, if there is overlap. The next is the intersection. The intersection is saying that A and B both occur. This is called A intersect B. Written A upside down UB, that's the notation. And this is the set of elements such that X is in A and X is in B. In the diagram, it's only the overlapping piece, right? So it's only the part where A and B overlap. Okay. Few more. In event language, to say that A, if A, then B, so A implies B, is to say that A is a subset of B. Written as A is a subset of B, like A is inside of B. And one way to say this is just to say that, well, if X is in A, then X is in B. As a as a diagram, let's see how many left. Got so as a diagram, what is this? This is saying, okay, A is in B. Let's call this B. Let's call this A. This is A. This is B. So B is bigger than A. Everything in A, everything that's in A is also in B. Okay. Next is A but not B. A but not B. So one way to say this is A minus B. So it's the stuff that's in A that is not in B. So we can write this as A minus B as sets. What is this equal to though? This is equal to A intersecting B complement, right? It's the stuff that's in A that is also in, that is not in B. It's the stuff that's in A that is in B complement, right? So it's X in omega such that X is in A and X is not in B. So what is that? That would be if I have A, let's do that. Make it a little easier to deal with, make it a little, nah. All right, let's start over. Let's make A here. B is here. Let's call this A, call this B. What is A not B? It's everything that's in A, but you can't count any overlap with B. It's this part. And then exactly one of A and B. It's called the symmetric difference. of A and B. It's written A triangle B. And the way that it's defined is it's saying, okay, let's first draw it and then let's think about how we would write it as a set in set notation. Oh, oh no. Oh, this is crazy. All right, come on. All right. All right, so one is A, one is B. Call this A. Call this B. We want exactly one of A and B, so that's this, right? This would be exactly just A. And then this would be exactly B. No, no overlap. You can't allow the overlap because we want exactly one of A and B, not both. So how do we do that? Well, it's A minus B, which we did above, and then we also have to add on B minus A, right? So it's A intersect B complement, or B intersect A complement. Finally, all possible events. It's the power set of omega. It's the set of all subsets of omega. It's written as 2 to the power omega. This is a set notation, even though it's a number in there. It's the set of all sets. Set of all subsets of omega. Okay. This is the set of all events. This is the domain of discourse of probability. So this table is very important and is something that should be kept handy, should be studied, should be memorized, and should be understood. And it's something that we're going to use over and over and over again throughout this course. These are the main ingredients that we build axioms of probability and everything that we do in probability on top of. So let's come back and we will start with the axioms of probability in the next